Okay, cool. So now I would like to go into LLM tool use and agent basics. So we have two agent things in a row. This time I'm going to talk about kind of basics, and then next time I'm going to talk about agents for like coding and web stuff overall. This is very timely because Anthropic just released a new model today that can click on your computer screen. So you can think about that as you listen to this. Cool, let's get started. So up until now, we've been mostly talking about systems that kind of process language in a vacuum. So we had things like language models that predicted text. But what I want to talk about this time is AI agents that iteratively perform actions in the real world. And LM agents are agents with an LM backbone. Before LM agents are kind of maybe the standard nowadays, but before LM agents, we had agents that didn't have a language model as a backbone and just were trained directly to, predict actions from images or other things like that. So that's what I mean when I say LM agents. So does anyone know what an agent is? Would anyone be able to define an agent? Yeah.
Takes in observations about an environment and generates actions.
Okay. Something that takes in observations about an environment and generates actions. Anybody else? Okay, that's a pretty good definition. I think there's a bit of disagreement about what agent or agentic means. My definition is pretty close to that. So one is that it proactively uses tools, and those tools are often used to observe or act in the environment. Another one is probably an iterative multi-step process. Maybe interaction with the outside world, although there are some cases where people have been saying like agent or agentic workflow or something like this, where it's not really interacting with something that's really outside of the current environment that the LM is or the current not really interacting with the outside. So I'll explain what I mean about that in a second. So if we think of what an LM agent consists of, when you say an agent, usually you're talking about the combination of three things. The first is an underlying LM. The second is a prompt that somehow, conditions the output of the LM. And the final thing is an action in observation space or a list of tools that you're able to use or something like this. And so when people say something like a multi-agent system, usually they're talking about varying one or more of these and having different models with different action or observation spaces or different prompts or other things like that. So if we think about whether one of these things is an agent, it's not actually super important, but if we think about an LM system that browses the web, that's probably yes, because it is iterative. It's interacting with the outside world by using a web browser. It's also using tools to access that web browser. One that searches for files on your OS and processes them using code. That might be one, especially if it's interactive in some way, but so I'd say that that's probably yes. An LM system that retrieves and generates, so like a RAG system, like the ones that you're implementing, maybe not. Maybe this would not be considered an agent because it's not incremental, so it doesn't do multiple steps. Although you could come up with an incremental system that might be considered an agent. And in a language model like O1 that has a very complex chain of thought, in general, this would be no, because it has no tools or interacting with the outside world. But if you gave it access to tools, then maybe so. Yeah.
What do you mean by tools?
I'm going to talk about that in a second. Yeah. Cool. So if we think about requirements for successful agents, I've done a lot of work in building agents, and they need to be able to use and access tools, which again, I'm going to specify in a second. They need to be able to represent the outside environment in some way. they need to be able to understand that environment. So they not only need to have a representation of the environment, but the LM actually needs to be able to process that into actionable representations. They need to have reasoning and planning of some variety. And they need to interact or communicate both with users and possibly with other agents in a multi-agent system. So first, I'd like to look at some agent use cases and environments, and there's a ton of them. Agents are being used in a lot of different places nowadays, but here are a few examples. So the first one is just in a chatbot. You can provide a chatbot with tools, and ChatGPT had a thing, plugins. This was very popular like a year ago. Does anyone use ChatGPT plugins now? I actually don't even know if it still exists anymore, but I created these slides about like 8 months ago or something, and then it was like very popular. Now not so much. But the basic idea was they got a bunch of companies, and the companies like Expedia or Instacart or whatever would create a plugin, and then you could plug that into ChatGPT, and you could get ChatGPT to like order food for you on Instacart or something like this. So that was a thing. And I would say that this is an agent for sure because, it's incremental. It's using tools to access the outside world. Another one is like navigation or robotics. This is not really my main area of research, so I covered this a little bit less here. But the basic idea is you have kind of a representation of the outside world, and you have navigation actions where you can navigate through that outside world. This could be, an autonomous vehicle. It could be a robot, other things like that. And all of those are also agents of some variety. Another thing is there's a lot of embodied agents in virtual environments, and these are particularly good as like a test bed. They're also good for simulation, for training things that will interact in an actual environment. There's famous data sets. One is called Alfred, and one is called Alf World. Alfred is a vision language environment. So you have a visual representation like this, and then you have actions that you can perform here. Let's see if I think I get a video. Oh no, this is a PDF, so my videos might be dead. Hang on one second. It's much more fun to do this with the videos. So let me open my Keynote. Okay. So yeah, so you have an environment like this, and then you can do steps through the environment. And you have like, your task is to examine an alarm clock with the desk lamp, and then you go to desk 1. And this is the textual representation, and this is the video representation from Alfred. So there's a bunch of these virtual environments nowadays. This is a kind of classic one by now from 2021, but there's lots of others as well. There's also a fairly large amount of work in games. And Minecraft is one of the favorite games that people have been building agents for. This is an example from MineDojo, which is a benchmark for doing things within Minecraft. And you can do things like craft a glass bridge, build an oak house, make an ice igloo, and other things like that. And then you have an agent that can kind of perform goals in this setting. Another one is software development, which I'm going to talk about more next time. So you can kind of put in something over here that says like go in and which one is this? Oh yeah, this is making a test. So basically you have an agent, and here this agent goes in and it does things like manipulate the bash terminal, write code in Jupyter, use a web browser, and other stuff like this. And right now it's doing things like creating a test file, making a directory and other stuff like this. And then it runs the code that it wrote and creates tests and stuff. I'm going to talk about this more next time, so I'll talk about it next time as well. Another thing is UI automation, and UI automation is basically doing things like going through web browsers, going through Android apps and other stuff like this. And generally what you do here is you do something similar to what humans do, which is like clicking on specific parts of the UI, entering text and other stuff like this. And as I mentioned, Anthropic just released something a few hours ago that also does UI automation, and they have some examples. And I'll be talking about this more next class as well. So these are examples of like tasks that you can do. But first, I'd like to talk about like some of the basics of how we can do these tasks with language models. And the way we do this is usually by providing language models with tools. And what I mean by tools here is it's essentially a program that you can use to interact with the outside world through a kind of functional interface. And so it's a function that you can use. One thing that's pretty important is this is a program that runs externally to the LM. So it's not relying on the LM's computation. So it's different from something like chain of thought, because chain of thought is essentially running inside the LM. And usually the way the LM interacts with this is it generates function calls and input arguments to the functions. And there's three main ways you can use tools. The first one is for perception. And what this does is this collects data from the environment. It can do actions, which exerts actions or changes the environmental state, and does computation. And all of these are tools. When we talk about an agent, generally we're talking about interacting with the outside world. So perception and action are particularly important. If you're just using tools for computation, that's arguably not an agent because it's not doing anything with the outside world. But that's just a matter of definition also. So, and here are some examples of tools that are pretty widely used. Oh, and one thing I should point out is all of this is from a survey paper that one of my students, Zora Wang, wrote called like, What Are Tools Anyway? And so that's in the references. You can go and read that if you'd like to get more details on any of these things. So the first thing that you can do with tools is knowledge access. And there's a lot of different ways that people do this. One is by doing things like executing database queries like SQL. So you run SQL and get information from a database. Another thing is running a search engine. So this would be just running something like Google or Bing or something like this. Another thing could be retrievers, where you are actually running the retriever yourself in a RAG style system. Another thing is computation. So computation could be things like calculators, Python interpreters, and other things like this, or like manipulating databases. And all of these things are kind of not even necessarily related to the external world, but they're performing things that language models are not very good at doing on their own. So for example, language models are not particularly good at doing complex math. Even the strongest models fail to multiply like 7-digit numbers together, which I do too, so it's not surprising. But language models are not good at this. They're very slow at doing this, so you can rely instead on programs to do it for you. Other things are interaction with the world, either through observing or acting. And so you can do like get weather, to get the current weather, get your location, fetch events from a calendar, verify whether an email address is an actual email address or not, things like that. Another place where tools have been used, it's maybe a little bit less important now that we are using multimodal language models, but they have been used for non-textual modalities. So you could do things like call an image caption or to get a caption of an image, or other things like that. Play music on Spotify, do visual QA. Another thing that people have done, but again, this is becoming less, you know, a little bit less important as we are working with more good general purpose LMs, is like have a separate QA system that can answer questions really well, or have a translation system that can do translation very well. So these are other kinds of varieties of uses of tools. So any questions here? Okay. So how do we get LMs to use tools? There's the first thing to know is what the way we generally use tools is we generally generate text, and then at some point we switch over to executing the tool, and then we feed the output of the tool back into the LM in some way. And there are two ways to cause LMs to use tools. The first one is to prompt them, and the second one is to train them, just like most of the other stuff that we've talked about so far. So how do we switch between just using an LM and using tools? There's kind of two major ways of doing this. The first one is to have a special token that is specifically created for calling a tool. And this kind of requires training. You must train the model if you're going to be using this method. But to give an example, this paper, they basically enumerate a whole bunch of tokens, and then they append these tokens to the vocabulary. And when one of those tokens is selected, they switch over to using that tool. So if you know in advance which tools you're going to have available, then this is a good method. Also, this is allegedly the method that's used in ChatGPT because Andrei Karpathy said so on Twitter. So he worked at OpenAI at some point. So I am kind of assuming that that's probably true. So ChatGPT has a very limited number of tools, so that makes a lot of sense in this case. The other option is to have something like code tags, where when you output that tag, you can output a program, and then after you output that program, you go in and execute the program when the tag is closed. This is a little bit easier to use with prompting style methods because you don't need to train any new tokens or anything like this. You can just prompt the model and say, please output execute Python, and then you can output Python in between these tags. And so this is another method that people can use. So how do you prompt for tool use? Essentially, what you want to do is you just want to tell a good instruction following model that it can use tools. And one way you can do that is you can provide it essentially documentation. And this paper gives an example of this. This is one of the papers by a PhD student who was in my lab, Xuyan Zhou, who graduated recently. But basically, the potential, you write some documents, and these are documents for bash commands. And then based on the documents for bash commands, you show these documents, and then the output will be like based on these documents because language models are able to follow directions well. Another thing I should point out is this is only really important when you're using special purpose tools. If you're using general purpose tools, the language models will also have already been like trained on them. So you don't actually need to append them to the prompt. So just to give an example, when we have a coding agent or something like this, I just ask the coding agent, please push this to GitHub. I don't need to give it like a GitHub push command, and it will just know how to use Git because it's seen it a million times before in its training data. So this sort of, the first thing you can do is you can say, you can execute arbitrary Python or arbitrary bash commands by putting them in between the execute Python and execute bash tags, and it will do a pretty good job of that. But further, if you have special purpose things, you can provide them through documentation. Yeah.
So for the code tag, how do you train the agent?
How do you train it? So in this particular paper, they try two different things. The first thing they do is they just prompt GPT-4. And they say, like, you can execute Python, and when you execute Python, put it between the execute Python tags. And that's enough for most strong instruction following models nowadays. But they also try a training thing where they generate, basically they curate a few existing agent data sets so that they're in this format, and then they train.
If it's a new tool, like ChatGPT knows executing Python, but if you want to train on a new tool, would this work?
Yeah, so I'm going to talk about training on tools, but combined together with prompting in this, what you can do is you can literally just say, okay, you have a Python library. This is the signature of that Python library. You could even provide a doc string or something like that and say, this is a tool that you could use, and that works. Yeah, yeah. That's what this paper is showing, basically. Yeah. Cool. Any other questions? Okay. So there's also methods for learning for tool use. I talked about this a little bit before, but I'm going to talk about it a little bit more in depth now. This is the tool former paper. And basically, the way they trained the model for tool use is they had a multi-step process. And they started out with basically prompting the model. So it says, your task is to add calls to a question answering API to a piece of text. The question should help you get information required to complete the text. You can call the API by running QA question, where question is the question you want to ask. Here are some examples of API calls. So they basically did few-shot prompting, and they used it to annotate the data like this. So they sampled all of these, and then they executed these. By the way, this was not by people in CMU, but for some reason the example's from Pittsburgh. But you have one other name that was Pittsburgh known by, what country is Pittsburgh in, and you have these things. And then based on this, they check whether that improves the likelihood of getting the next word correct or decreases the likelihood of getting the next word correct. And they only annotate with tool calls that increase the likelihood. So essentially, it's like an RL style training approach. And there's other ones that are similar to this too. Cool. So this is how you can create data. Of course, you can also create data manually. So you could annotate data manually. One thing I'd like to point out is tool use is now very widely used. It's like a very, very important part of practical systems. And this actually isn't talked about that much in like research papers or things like this, but a lot of people who are building LLM style applications use this very heavily. And there's even a standard that was created by OpenAI, but adopted by a lot of other models, including open source models, where you essentially define tools in a Python kind of list of dictionaries. So you have the name, which is like get delivery date. You have the description, which says get the delivery date for a customer's order, et cetera, the parameters. And then when you pass this into the completions API for OpenAI or whatever else, you add the tools here. And if you do this, then it will be guaranteed to output the tools in an appropriate format, or it will encourage the model to output tools in the appropriate format and stuff like this too. And the reason why this is the case is because undoubtedly behind the scenes, they're using these sorts of methods for training the models. And when they train the models, they make sure they pass in the prompt in this format and the output is in the appropriate format and stuff like this. So they're training the models to accept this, the inputs in this format. Cool. Any questions here? You can definitely look at, if you're interested in open source models that are good at doing this, there's other ones, like, for example, Command R is a model from Cohere that was trained in this way. Noose Hermes is a model that was trained in this way and stuff like this. So if you look for like tool use in open source models, you can also find models that kind of follow the standard. Cool. A final thing that I'd like to talk about is up until now, I was talking about tools that already exist and you're incorporating into your workflows. But there's also a paper that we wrote recently called Trove, which tries to induce tools. So you start out with kind of a stream of data. And based on that stream of data, you have a whole bunch of examples. You run it through a coding LM. You output a whole bunch of solutions. And based on this solution, you also output a set of tools. And so the way you output tools is you ask the model to define a function and then use the function to solve the problem. And then if defining the function and using the function to solve the problem results in a better result, then you have a new tool and you can add that tool into your toolbox. So and it will output something like calc rate of change. And then next time you can use this calc rate of change tool in order to do a better job. So it's a little bit like Toolformer. If you think about it that way, so like Toolformer, basically what it was doing is it was adding function calls into text to improve their ability to do a good job at modeling the following text. Trove, what it does is it generates functions that are used within code, and then if those functions improve the results, then you add them back to the toolbox. How do you know if they improve the results? If you have correct answers, then that's relatively easy. You just look at the output and see if the answer is more correct when you use the tool. But even if you don't have the correct answers, there are ways you can judge whether the result looks better. So for example, in the paper here, we use consistency between multiple sampled results. So if we sample like 15 results and it's more consistent, then and the one that uses the tool is more consistent, then we assume that that's like a quote unquote better result. Cool. So that's one big part of agents, giving them access to some variety of tools. Are there any questions here for discussion? Okay. So next, I'd like to go into environment representation. So environment understanding is really important. The agent needs to understand, in order for the agent to understand the environment, it needs tools to access the environment, like in the last section. It needs a representation of the environment and methods for holistic understanding and exploration. And there's a bunch of ways we represent environments. The first way we do it is just through text. So this works for things like a text game. So this is an example from ElfWorld. It also might work for like an iterative RAG-based question answering system where like just every time you provide new information through RAG and you iterate over it, you get more information until you're confident in the result. So text is very, very common as a representation. Another environment representation is images. So I already gave this example of touchdown. But this is a case where you're navigating in the real world and you don't have access to any text. It's just images. You're just walking around in the real world. This is all you're able to use. There's a number of problems with image representations, though. So in order to perform well as an agent, the details matter a lot. And to be honest, I feel like image understanding is far behind textual understanding in terms of understanding all the details of like images, videos, other things like this. And just to give one example, OCR, character recognition in transcription doesn't work perfectly. Grounding over complex layouts also doesn't work perfectly. And it's especially bad in open source models. The closed source models are actually kind of okay at this. But open source models had been very far behind for a long time, and they would not be able to recognize the text in web pages. They would not be able to select the correct buttons. We just recently on Monday, or no, sorry, Friday, Friday or so, released a paper where we trained a model on lots and lots of web pages to try to make this a little bit better. And I assume that like OpenAI and Anthropic and other places like this are also doing very, similar things. But basically what we did here is we took advantage of the fact that web pages, we know the underlying representation of the web page. And that is something that language models can actually process quite well. It's like a web page HTML. They do a pretty good job. Like OCR is not a problem because you already know the characters and they do a pretty good job of understanding it. But we can then go and render an image that's relatively hard for an open source model to understand. So what we do is we generated a whole bunch of auxiliary tasks from this. And so then we can take the image and we can predict, we can answer questions, or we can take the image and say something like, I have labeled bright IDs for some HTML elements in the website. Tell me which one I should click to complete this instruction. Learn about the animal of the day. And then it would pick C. And all of these can be generated from text-based language models by just looking at the HTML. So that allows us to create, essentially infinite training data for these sorts of understanding things. And we demonstrate that this works a lot better. So again, like I do think that the closed source models were maybe already doing something like this, but this is an example of how you can improve understanding of images. Cool. Another variety of environment representation that's used for web navigation is either directly, so you can use screenshots, but they have their problems, as I mentioned before. You can also use HTML, like web page HTML. But the problem with HTML is very verbose. So you'll throw it into a language model and you'll use up your token limit. You'll run out of context and stuff like this. So there's two ways that people resolve this. The first way that people resolve this is there's actually something called the accessibility tree. And this is used in screen readers for people with vision impairments, basically. And so the idea is this has taken out all of the kind of verbosity and complexity in the HTML and kind of condensed it down to like the smallest possible amount of information to still fully understand the whole web page. But this can still be verbose, especially for really big web pages. So another thing that has been done further, I actually don't have the reference on here, but it's done in a paper called Mind to Web, is you can actually predict which parts of the web page are relevant based on the current intent. So you can further filter it down and filter down to only the relevant parts. So this is used pretty widely as well if you want to use like a text-based language model for web page understanding. There's another, and this was done in a paper called Web Arena that we did. There's another paper called Visual Web Arena, and in Visual Web Arena, they used visual representations to understand web pages, also C-app and others. But actually, they found that using the screenshot and the accessibility tree at the same time, using both of them as input was kind of superior to using just the screenshots as well. So this is still having the textual representation can be pretty helpful for most language models. One thing I'd like to point out is this also applies to other varieties of documents. So like PDFs, whatever else you want to use as well, because you can usually get the text directly from them. Finally, another important kind of advance that's used pretty widely in these models is something called set of marks. And set of marks is where they basically do some variety of object recognition, and then they mark each object with a number. So if it's like, I want to go to this chair. There's 2 chairs in here, so it will say, I want to go to chair 6. And this, for things like GPT-4o, this is actually pretty easy. And for web pages, they also do set of marks over web pages where all of the interactable elements are like surrounded by a box, and then you put a number next to it. And that's how web pages are generally represented visually when you want to interact with them. Another thing that you can do, and there was a recent paper from Ohio State and also the Anthropic demo that just came out today does this, is you can just say, I want to click on this pixel. Like this, I want to interact with this pixel. You can do that, but my general experience has been that this is pretty hard to get to work. It's much easier if you have something like this set of marks because there's less room for error, like your action space is smaller and stuff like that. So that's another alternative way of taking actions here. Cool. So this was environment representation. Any things that people would like to follow up? Okay. So I'll go next to environment understanding. So this is a really big challenge. Like what I would say is this is really important. Environment representation, getting good models that can like take in an image and understand it well. Good models that can take in accessibility tree and understand it well. This is still a very big problem, especially in open source, but even in the closed models. But I would say that this is more unsolved. And models, at the moment, models don't know everything about the environments they interact with. And there's some knowledge that's included in LLM parameters. So for example, things like coding, LLMs know a lot about coding. They also know about things like navigating popular websites. They might have a small amount of common sense about like, I don't know, a McDonald's menu or something like this, like world knowledge that's useful in agents. But much of the knowledge about the environments needs to be discovered on the fly or provided in some way to them. And so if we talk about all the environments, we're talking about like navigating Amazon, navigating an Amazon web page or something like this. How well do language models know how to do this? So the answer is they don't know how to do this very well. And a very big failure mode of agents is that they end up just like going to the wrong page to solve a problem or something like that on a website, for instance. So one way that people overcome this is by just manually crafting prompts to do a really good job in the environments that the agents are tasked with. So just to give one example, there's this paper STEP that has very good results on Web Arena, which is a web navigation benchmark. But basically what they did was they created a whole bunch of prompts that could be used at appropriate times when they want to solve particular tasks. So I know this is small, so I can read it, but it says, please, when you want to search issues on GitLab, this is the search issues policy on GitLab. It says, please follow these instructions, navigate to the issues page. Once you are in the issues page, you must first navigate to all issues so that you see both open and closed issues for solving the objective. You may not see all issues listed at once. Use the search bar to search for appropriate keywords and filter down to the relevant set of issues. If the objective says to open ... issue, check if it is X. You must first open it. So you get the idea. It's very, very detailed instructions about how to do a specific thing on a specific website, GitLab. So this raised the accuracy from 15% to 35%. So it's very effective. But the problem is, like, what if you wanted to do a different website? That's, it's not going to generalize very well. I can give another real world example too. So the coding agent that I am developing and I'm going to talk about before, we're using the coding agent to improve the coding agent. And so in order to do that, we want instructions about how to navigate this repository. So for this repository, we have information about like general setup. This is what you need to do to set it up. This is where the backend is located. This is where the front end is located, and other stuff like this. So if you provide this information, like the agent, even if it hasn't ever been trained on this repository or know things about it, kind of gets a general idea of where to go. And these can be added through prompts, et cetera, and things. Cool. So that's one thing. Another example that we can do here is unsupervised induction of prompts like this. And so generalization is the problem. So why can't we just induce these prompts automatically? And the way we did this is, and this is another paper by Zora who did the Trove work. And the way we did this is we essentially did something very similar to Trove. But instead of inducing tools, we basically induce prompts for specific workflows that the agent wants to do. So what we do is we have the agent perform a task, and it will click through and do the whole task. This is for web navigation tasks. We then check if the task has been solved correctly. And if the answer is yes, then we do that. If the answer is no, then we don't do this. For Trove, we did this through like self-consistency between the answers, but for this, we just like mostly asked a language model whether the task looked like it was solved appropriately, and if the answer was yes, we said it was solved properly. Then based on that, we split it down into workflows. So we ask a language model to divide this into like different workflow steps, and then we add this back into the memory. And we did this on a website by website basis. So we did it for individual websites. And because you do that for individual websites, you can end up inducing prompts that look a little bit like this, essentially, that are like, first, in order to open an issue, or in order to find existing issues, I did this, and then I did this, and then I did this, and then I did this. So it's a way to kind of induce these automatically. So I mentioned that step with the manually curated things. It went from like 15 to 36. Agent workflow memory with the automatically induced things went from 15 to 35.5. So we didn't quite match human performance in terms of prompt engineering, but it's pretty close. So I figure that that's kind of one level of improvement that you could expect from better environment understanding on these complex environments. Yeah.
Does the language model do a good job on evaluating trajectories?
Does the language model do a good job on evaluating trajectories? This is a great question. I think it's much easier to evaluate trajectories than it is to generate them. It's still not perfect. And I have a lot of firsthand experience because I like use coding agents in my everyday work. And I'll talk about this a little bit more next time, but I would guess that in my personal experience of asking AI agents to do pull requests, it's like 70% both precision and recall. And what I mean by this is it gets it right 70% of the time. 30% of the time it's a false positive where it said it was actually correct and it's not. And 30% of the time it's a false negative where it said it was not correct, but it actually was. And the biggest source of false negatives for like coding stuff was that like it finished most of the problem, but like the final details were not correct, but it's still mostly like, or it couldn't run tests, or the code wasn't like immediately running in the environment because the environment setup failed, not because the code was wrong. So there's also examples like that. Yeah.
Because like the bottleneck was environment understanding. I thought it would also be tied with evaluating the trajectory itself.
Yeah, that's a good question. So the bottleneck, if the bottleneck was environment understanding, wouldn't that be tied with evaluation? I think the answer is actually not really. And like, if you think about the problems, if you think like, just look at this example of a prompt, like you can kind of tell if you look in hindsight and if you look at all of the like steps it took, you can kind of tell if it found the issue appropriately. But you it doesn't know how to do it. So I think judging is definitely easier in this case. It's not always the case. Like it's sometimes judging like fake images is really, really hard. But like in this particular case, I think it's easier. Yeah. Cool. Okay. Another thing is environment exploration. And environment exploration is something that you do before you even start solving a task. And there's a lot of this. If you take an RL class, this is going to be like, there's going to be whole like sections on this. But the basic way that you can do this is give the agent a sense of like curiosity. And what I mean by curiosity is like you reward the agent whenever it discovers new things, or you continue the agent on the trajectory when it starts discovering new things. A very famous paper on this was by Deepak Pathak, who's actually here at CMU now. And they came up with an objective function for RL agents where you give it a reward anytime it's hard to predict the environment. So anytime you're in a place in the environment where it's like a language model is not able to accurately predict the next, how the environment is going to change, then that's a section that you should be exploring more and understanding better. So there's methods like this. Specifically within LLM style agents, this is one example. And the way it works is essentially they sample a fake instruction, and then they have the LLM agent try to perform the instruction in the environment that it's in. And so you might give it the GitLab top page and say, please go open an issue on the bagel repository that says I need more bagels or something like this. And if you did that, the LM agent would then try to go execute that action. But the problem is, what if there's no bagel repository? This might fail. So the LM agent might go and do something else. It might go like open an issue on a different repository or something like this. So then they have an LM-based labeler to go back and relabel the trajectory and say, actually, it looks like the trajectory was doing this. And so they have this like iterative refinement process where they like automatically create trajectories by going back and forth with this kind of like exploration. And so that's one example. Cool. Any questions here? Okay, so another thing I'd like to talk about is reasoning and planning. There's a fair amount of work in this. I'm just going to kind of go briefly through some of the very representative works. But the most representative work here is something called React. It's actually fairly straightforward. The basic idea is you had LLM agents and you had a chain of thought, and we stick the two together. So we provide LLM agents with the ability to perform chain of thought before they pick their next action. And so you have thought, like you would have thought number one, I need to search Apple Remote and find the program it was originally designed to interact with. And then the actual action is search Apple Remote. And basically, they demonstrate that this gives you a lot better accuracy, a lot of improvements. It's also better for interpretability. So like I can actually give a concrete example back from our software development agent that I showed here. Oops. So here I put in like the thing I wanted it to do. And we're also using a React style framework here. But what you can see is it says like, certainly I'll clone the repository. First, let's clone the repository. So that's the thought. And then the action actually gets executed over here. And they're like separated by tags, right? And so that's good because you can look on the left side to kind of see what's going on at a high level. And then on the right side, see the actions that are actually being provided. So it's kind of important from two different levels. So another thing is global planning. And this is a tricky one. It's very nice from one point of view, but it's tricky from another point of view. And basically the idea is this is the simplest example, which is where you say, like, let's first understand the problem and devise a plan to solve the problem. Then let's carry out a plan and solve the problem step by step. And so this is just relying on the like few shot learning ability of models, or sorry, the instruction following ability of models. And they end up generating a plan beforehand and then executing on the plan afterwards. And this one was used like just to improve chain of thought, but there's lots of other examples of this in from the point of view of agents as well. Yeah.
So for the previous one for React,
Yep.
The context can quickly blow up, right? Like let's say you have like longer chains of reasoning with like 20 steps or something.
Mhm.
You wouldn't necessarily need all of the previous steps. So are there ways to like summarize the previous steps or something like that people like use generally?
Yeah, it's a great question. So the question was for this would end up being like a very long, context to be using, which might be inefficient, right? That's the main worry. So are there ways to summarize? Yes, there definitely are ways to summarize. I don't have them on the slides here, but asking a language model to summarize is the most common way. There are actually toolkits like MemGPT that try to like implement this sort of summarization style method. For web pages, this is an even larger problem because web pages are very, very verbose, and putting all of the web pages in your memory is going to overflow your context limit. The thing is, this is actually really hard, I guess, because you kind of, if you summarize and then throw the old stuff away, you might be missing some important stuff in the past. And so at the moment, what we're doing in coding agents, for example, is just not summarizing anything, keeping everything around. And we actually tried incorporating this sort of summarization technique, and it was dropping performance. So I think there probably are good ways to do this, but it's maybe a really good kind of direction for research in order to find out exactly how you could do it. I think another thing that could be done is incorporating RAG in some way over the memories. And I think it's a relatively straightforward like idea, but like the actual execution of doing that is pretty tricky. So yeah. Cool. Any other things? Okay, yeah, so this is another thing where the idea is straightforward in theory, but the execution is difficult in practice. And the reason why is, at least from my experience, language models tend to be very faithful to the prompts that you provide them. And because of that, once it's created a plan, it will execute the plan, no matter how bad the plan is. So if you say you need to do step 1 and step 2 and step 3, and then step 1 is not working for some reason, it will, get stuck there. So you need essentially ways to revise, which I'm going to talk about in the next slide. So another really important thing is error identification and recovery. And agents make mistakes all the time if you give them a like reasonably difficult thing to do. And the kind of representative method that discusses how to fix this is reflection. And reflection, basically what it does is it executes an action and then it gets some sort of environmental feedback from that action. And then it goes and takes the next action based on the environmental feedback. And they experiment with this in a number of different settings. But yeah, this is important. I think one really difficult thing here, though, is how can you identify like between better and worse things when you don't have like 0-1 environmental feedback? And actually, I realize, sorry, I just realized I didn't make a slide for this, but I'd like to talk about it anyway. So there's this really nice paper also by JY here at CMU on tree search for language model agents. And the basic idea is you have a state, like value assessor. I forget exactly what they call that in the paper here, but basically you take a step forward and then you take multiple steps forward, and based on the multiple steps, you kind of assess the value of the current state, and you keep certain high value states alive and search forward until you eventually get to a good solution. And this is using a method called Monte Carlo tree search that some people may have heard of. And you essentially sample more high value states, with the idea being that you'll eventually find a successful state if you do this. I had a question before about whether assessing success is easy or not. And I said, I think assessing success is relatively easy. Assessing progress, I think, is hard. Like telling whether you're going in the right direction is difficult. So if you want to do some sort of thing like this could definitely be very useful. But having a very good measure of assessing success is going to be key to making these methods work better. Another problem with doing this sort of thing is a lot of actions are actually not reversible. So if you take an action forward and make a mistake, then, like, for example, let's say you accidentally bought a plane ticket. A lot of plane tickets are not, refundable. So you would not, that would be very low value if you bought a plane ticket to a wrong place, but you wouldn't have a way to get around it, or you might have to call a customer service agent to get around it or something like that. So that makes it difficult to roll back. So there are ways that you could think of getting around this, like, imagining what the future state might look like if you clicked on that action. But that's, more difficult and not covered directly in this paper. And also how to come up with better value functions. How to do good rollback in like complex and interesting environments. So I think this is a very interesting paper that opens up a lot of ideas, and you can take a look at that. That sounds interesting. That being said, it's complex and expensive. So if you don't want to burn through too many API credits or GPU hours, you might want to reconsider this one, but it's interesting nonetheless. Cool. So the final thing that I wanted to talk about in the planning section is revisiting plans. So as I mentioned, like once you make a plan, language models tend to stick to them. And there's one paper that I saw recently that does have a planning step, but it also has a step where you can go back and like revisit the plan. So you essentially delegate. You have a global planner that comes up with a plan. It splits that plan into steps, and then it delegates those steps to a local agent. The agent tries to execute on that step, but the local agent also has the ability to say, this is impossible, I'm not able to do this, and kick it back up to the global planner. And if you do that, then the global planner can go back and revisit the plan. And so I think if you want to come up with a planning style agent, something like this is going to be really necessary, because I've tried simpler techniques and they don't work well with kind of a fixed plan with no flexibility. Cool. So another thing I'd like to talk about is multi-agent systems. And in these cases, we have multiple agents interacting with each other. And if you remember right at the very beginning when I talked about multiple agents, or no, actually, sorry, I'll talk about that in a second. So multi-agent systems, there's several reasons why you would want to do this. The first one is defining the problem structure. The other one would be providing the right knowledge at the right time. switching between LLMs, providing security or safety, or simulating human interactions. And I can talk about these one by one. So the first is defining problem structure. And this is like one simple example of this is where we had the global agent and the local agents. So there we had a global agent, which its only job was to create plans. And then we had local agents that went and executed on the plans. So this is like not very fixed problem structure. It's more like, mostly defined by the LLM. There's other ones where, for example, you might have a planner, and for something like web navigation, you might have a planner that can delegate to a browsing agent, or it could delegate to a Amazon agent or a GitHub agent or something like this, where each one of those had a special, prompt to work there. Or maybe each one had a special LM that was tuned on Amazon specific data or something like that. So that would be one way to do things. Similarly, providing the right knowledge at the right time. So like that's another example. You have Amazon agent or a GitHub agent or something like that. Also, there's security and safety. So some people have said that, let's say we have a database access agent, and that database access agent is able to access a database that you don't want any information leaked from or something like that. So you could have the database access agent is the only one that has access to the agent, to the database. And then your overall like planning agent or task execution agent can make a request to the database planning agent. And then you somehow have kind of security safeguards or other things like that. Like the database planning agent can't return the database credentials or something like this. So that would be another thing that you could do. And then finally, there are methods to simulate human interactions. And so this could either be simulating the interaction between a human and a system, or it could be simulating the interaction between like many humans, for example. So these are some other examples. So I think there's advantages and disadvantages to multi-agent systems. And I've actually tried to use both in engineering like systems that I want to work, like web browsing systems and coding systems. And they can explicitly define the structure, but on the other hand, they can be overly rigid. And so, for example, we have a setup where we have a coding agent and we have a web browsing agent. And the coding agent delegated to the web browsing agent. And then the web browsing agent wanted to do something, but then the web browsing agent wanted to code. And so the web browsing agent is not able to code, but it knew it had to code to solve the problem. So it opened an online coding website and tried to start coding on the online coding website, which was very creative solution, but it's not a very efficient solution because it got blocked by the robot blocker and stuff like that, and then wasn't able to code. So by defining the structure, there are advantages, but also disadvantages if any like eventuality comes up that you didn't think about in the first place. Which is what I just said. They allow for more flexible credentialing, but they're also not a silver bullet because still you have this agentic system, and language models are surprisingly creative at finding out ways to get their jobs done. And so even if you have a multi-agent system where you thought you were able to, secure something, they might be able to like ask the database agent to extract, the password and turn it into like bytes instead of like ASCII or something like that, and somehow that manages to get around the safeguards of things. So I actually have a blog post about this. I don't have a paper, but you can look it up on the references. And so I've also found other alternatives to multi-agent systems using single agents. So if you want to define problem structure, actually coming up with descriptive prompts can go a long way to do this. So think about your multi-agent system and all of the things that you would have put into your multi-agent system and just concatenate them together into one prompt. And language models nowadays have a long context length and reasonably good instruction following abilities, and they're able to do this. Providing the right knowledge, I think using retrieval is a reasonable way to do this. So like, instead of having an Amazon agent and a GitHub agent, you could just have one agent that can retrieve the APIs from all of them. Switching between LLMs, I think, is a very good use case because you could get like a higher accuracy or higher accuracy or lower cost. But we did also talk about model routing techniques that should be able to do this in a more general way. Providing security and safety, my current solution to this is credentialing the whole system, not individual parts of the system. So I think you need to be careful about security regardless of whether you're letting a single agent do it. For simulating human interactions, there's not really a single agent solution. So I think this is the one place where definitely you would want a multi-agent system. For the other ones, you might think of other alternatives. Regarding simulating human interactions, I can give one example of a work that we did here, which is maybe, or actually, why don't I give two examples? So this is one example where essentially they created a little town of agents that walk around and interact with each other and buy things and stuff like this. So it's kind of an interesting kind of toy setting where you can get agents to walk around and talk about things. This was further scaled up, and this is called generative agents. So this is another one that was created by a startup that's even further than this. They have like a whole bunch of AI agents that interact in Minecraft. It's from a startup called Altera, and they learn to cooperate and stuff like this. So it's mostly just a video as opposed to a paper or something, but it was kind of fun to see that. And then separately, we have a paper from people here at CMU. Satopia. And it's actually several. And this is a way to measure like social intelligence of agents. Sorry, the paper link is surprisingly hard to find on this. But the basic idea is that the agents communicate in kind of like socially charged scenarios. So it's like when two people would need to negotiate together or something like this. And it measures the ability of LMs to do things like negotiation or cooperation or other stuff like that. So I think these are kind of things where multi-agent systems can definitely be useful. Another interesting thing is so this is an interesting paper, and basically one of the things they ask here is whether agents can be used to kind of simulate human behavior and simulate social science experiments. And the answer is not necessarily, not at the moment, because language models are different from humans in a number of ways. And there's a bunch of other papers that look at this as well. But yeah, I think this is definitely an interesting area of research that a lot of people are working on. Cool. So that's about what I had to talk about today. Are there any questions or follow-up? This is an area that I like and I think about a lot, so I'm happy to discuss more if there's any